Okay, thank you, Peter, and good morning. Can I just check, is this all right for volume for everybody? I'm not hearing no, so I'm going to carry on. So I'm one of the EM scientists at EBIC, and I'm going to give our facility update this morning. And I think quite a lot of you were here yesterday for our user meeting, and you've heard Katie and Alan giving updates on our user program and our computing. I'm going to give the update on our technical developments over the last year, but I'll be touching on a few of the same things that they were talking about yesterday. So just to start, this is our current suite of microscopes. So EBIC is essentially split into two parts. We've got the industrial group, and they've got their Krios and just installed or installing their Scios screening instrument. On the academic side, we've got our 4 Krioses, plus we've got our Scios dual beam instrument, which we put on the user program during this year. And I'm going to talk a little bit about that in the second half of this talk. We've just had our Aquilos dual beam installed over the last few weeks. And we also have our Talos, which is our in-house screening instrument. So this is our Krios hall here, which is housing Krioses 2 to 5. One, if for anybody who knows the site, is still positioned over in the synchrotron ring. And during last year, we've upgraded. So we've got direct fill from the house liquid nitrogen lines to all the microscopes. So vacuum insulated lines, and this was installed with AS Scientific, and that the microscopes are filling very rapidly within 10 minutes, and there's a huge safety benefit to this as well. So we'll be looking to move our 200-litre dewars out of our Krios hall. And there's also automatic shut-off for the whole lines running to all the microscopes in the event of any oxygen depletion events. And that's also coupled to an autodialer as well, so the microscopes don't unexpectedly shut off and nobody knows about it. So at the bottom here you can see our control room, and we've got controls for all 5 of our Krioses plus the Talos up there using Thermo Fisher's fibre solution for that. Now recently we've installed K3 detectors on Krioses 3 and 4, plus the industrial Krios also shipped with K3. And just one thing to note on the installations, we have the 3 PCs for the K3s sat not in our Krios hall. We've moved them into our comms room, and that's work that's been done by Martin Howe at Diamond. So there's essentially for K3 servers, there's 500 gigabyte per second fibre links running 70 metres from our Krios hall to the communications room. And Martin, I think, wanted me to stress that this is using generic fibres rather than Gatan's proprietary solution, so it has probably saved us a fair deal of money doing this. Our K3 on Krios 4 was the first one that went onto our academic user program, and this is Dan, who's been primarily responsible for managing the installation and commissioning of this K3. So I'm just going to share some of our initial observations and experiences since we started using this over the last few months. So K3, the DQE is pretty comparable with the K2, but there's considerably faster readout, and it's roughly a 6x4 chip, so we're looking at larger acquisition area. But the main advantage in terms of throughput has been the much higher dose rates used for counting before running into coincidence loss. So this is the range that's been recommended from Gatan. We're typically collecting at around 20 electrons per pixel per second, and that's giving exposures in the order of around 1 to 3 seconds. We're doing all the automated data collection on Krios 4 using cryo-EM, and clearly one of the biggest implications has been the amount of data that this is producing. So as default now, we're saving as unnormalised LZW compressed TIFFs and then doing gain normalisation during motion correction. And given that there's frames are automatically written out in super resolution format, so 12 by 8K. Saving size is obviously a major concern, and there's around a 10-fold benefit from using this method. And as Colin briefly mentioned earlier, we're using a Relion pipeline to process all of our K3 data. I'm not going to say too much more than he did about that. So to say that he introduced there's a nice straightforward interface at the front for putting in the details from the data collection, pointing towards gain references and things, and then it runs through and then picks up and submits in batches jobs running through to 2D or 3D classification. So it's giving the genuine readout on data quality as you're collecting, and that's been working absolutely brilliantly. So on to the throughput that we're getting. So for typical 5 shots per hole data collection, focusing every hole and so collecting 1 hole from a stage shift, that's already up to 170 movies an hour. You can see the rest of the stats for different collections there. But also looking with CCP-EM to do so image shift data collection, collecting from, at the moment, up to 9 holes surrounding the initial hole with a single stage shift. And that's getting now up to, with that setup, up to 365 movies an hour. So we've got test data sets that we've taken with this, and this is a slightly truncated version of the summary of the full data set. So you can see for the initial hole and then a sample shot from each of the 5 surrounding holes that were collected from, using everyone's favourite apoferritin. And you can see the major consideration with the image shift collection is the effect of the beam tilt. So actually fairly minimal with the 5 shots in the central hole, but it's increasing with the peripheral holes here. And so doing the beam tilt correction in Relion 3, you can see that so the refinement with CTF refinement with beam tilt correction and just with CTF refinement only, we're looking at sort of around half angstrom difference. Just looking for that the shot in that position, and you can see the effect on the B factors there as well. And looking at the whole combined data set, you can see this is 3-hour data collection with this setup, so 5 holes, 5 shots per hole. That's given 120,000 particles. See nice little class averages down here. And really, I think the resultant map kind of speaks for itself in terms of the capabilities of the K3 and the fact that the effectiveness of the beam tilt correction with the image shift collection, and that's gone to 2 angstroms. I think whenever you can see the holes in tyrosines, you're in a good place. And additionally, we've also done data collections doing on-the-fly beam tilt correction in CCP-EM, and again, that's looking pretty effective. It's ribosomes now. See again the map here. A nice fit, and that's around 2.6 angstroms. So on Krios 3, we've also got K3 installed, and this is the first K3 that's fully integrated and embedded within EPU that went onto the user program in March of this year. And in terms of rates of data collection, it's approaching what we're managing with CCP-EM for single shots. There's some slightly different collection parameters here. The resultant figure is actually the same as we've got, but this is with slightly less focusing. It's a fraction slower, but still not too bad. Otherwise, works like EPU has always worked. There's some slight issues I think you can see at the moment. It's still in beta version, just with scaling and dynamic range of the lower mag images, but otherwise it's all working very nicely. So far we've been collecting with MRC format. Now this is giving sort of pretty huge stacks, so 50 frame movies over 5 gigabytes, with the rate of data collection, we're looking sort of potentially 10 terabytes or so in a day's collection. So there is the option already to reduce around fourfold with unnormalised TIFFs, but we're hopeful that there'll be the introduction of compression again here. So the reason we haven't used the TIFFs at the moment is we're expecting there might be some slowdown in the rate of data collection because it's writing out natively in MRC format and then converting to TIFF. So that's something we're looking to test a little bit as well. And just, again, validation test data sets, apoferritin again. So that's averages. And this is really not chasing resolution at all. This is more just validation of the fact that everything's working well with the collection. So it is 2 hours of data collection and an afternoon on CryoSpark, and it's still going nicely under 3 angstroms. So one of the main things I wanted to go on to today was to talk about the Scios user program, which we've just introduced, which started in October of last year. So I should say this is James, who has been essentially in large part running the user program, as well as running the Scios itself and producing the lovely looking Lamella. So just to introduce the instrument, we're doing loading for cryo with our quorum stage. We've got SEM beam and gallium ion source, and we're using sort of these kind of parameters. And so the final thinning stage with the fib beam, we're going down to a beam current around 30 picoamps. Now, a typical day's Lamella preparation will produce between 4 and 8 Lamella, and really the big determining factor for this is the quality of the sample, so the density of cells and in particular the ice thickness and condition of grid, and that really takes it from the lower end of that estimate up to the top end. So for users coming in, really screening is the absolute key to getting the most out of your sessions. So as I say, we had a commissioning call for our user program. There were initially 3 sessions really to allow us to test out the structure of these visits, all looking at cellular material, and you can see the structure here. So there's 3 days of milling on the Scios, Monday, Tuesday and Wednesday, and then we'll transfer over to the Krios to do tomography for Thursday and Friday. Now for our tomography, we're doing CCP-EM for all of our collections, and we're using WIM's dosimetric scripts for that collection, which I'm sure a lot of people have been using. We've made a few slight modifications as well to make it more amenable for Lamella collection. So as the milling angle puts the Lamella and sample at an angle, so when it's at stage 0, the Lamella's not going to be at 0 degrees. So we've added an offset in so we can go symmetrically around a pre-tilt angle. So we're giving the larger amount of the first bit of the dose to the actual part that's orthogonal to the beam. And we've also played around a little bit with the group sizes as well, because the effect of having this pre-tilt in means that for a symmetric collection, you're hitting the limits of stage tilt on one side a bit quicker. So we've got final groups that are smaller sizes. And typically we are using groups for collections. It's a little bit up to users coming in, but just to help with throughput. And additionally, 2 of the 3 sessions so far have been using faceplate for some of their tomography. So we're using Auto UI2 for that, and script from Chenzu. Our throughput is roughly around 45 minutes for a tilt series. So here we can see a pretty typical setup here. So we've got medium mag montage of our Lamella, setting up our batch positions to collect from, and really we're using some pretty standard tomography workflow for this. We'll take 4 or 5 grids typically that we've milled on the Scios during the Monday to Wednesday. spend the first morning setting up the microscope and detector, and then by around lunchtime, low magnification of the montage of the first grid to identify the lamella positions, and then medium mag montages of the lamella with conditions that are sufficient to be able to identify the targets that we're looking for to collect the tilt series on. So we'll run that through the afternoon, and then sort of mid to late afternoon, load the second grid. Typically we use the one with the most potential positions on it, and set up batch positions overnight, and then collect on the remaining grids on the second day. So hopefully at the end of it we've taken our cells, we've milled, and we have got nice looking tomograms, as we see here. So just to summarise this initial commissioning call for the Scios, the visit structure in the way we've organised it has seemed pretty successful, in as much as we've got the right amount of milling for the amount of tomography time, so that's something we'll look to replicate. So on average we're producing 4 sort of 10 suitable lamella in each milling session. That is including one lost session where the Scios went down. There is an attrition rate, and that's been around 9% for lamella that haven't survived the transfer steps onto the Krios. And on average, across the 3 sessions, we've collected 1.5 tilt series per lamella. One of the major limiting factors has been presence of ice contamination. Now, actually some looking very clean, but it is one of the major problems coming up against with the fib milling. I'll also just summarise that here, and you can see, yes, got this figure of 1.5. I think as we've got used to the structure of the visits and probably got a little bit more experience, I think you can see we've improved our output as we've gone through the 3 commissioning calls, and the most recent one yielded 27 tomograms, which is roughly what we think is around the optimal that we'll be aiming to replicate if we've got suitable samples in future visits. And coming on to future visits, so we've got the second call, which will be going out pretty much any day soon, so keep eyes peeled for that. Again, it's on-grid lamella preparation of cells. There'll be 5 visits this year, starting in October, and James has asked me to stress that ice thickness and cell density is really important. That has to be demonstrated. He's very keen for people to contact him if they've got any questions about this, so don't hesitate for that. And moving onwards, the future of cryofib at EBIC is apparently James, but sat next to him is our Aqualos, which we've just had installed now, and we're really hoping that's going to improve our throughput with the fib milling. So be looking to use semi-automated kind of batch collection for preparing the lamella. Still need to do a lot of testing and commissioning on this. The hope is we might be able to produce somewhere in the region of up to 20 lamella within a day. And also just to say, we're using MAP software, so that's going to have sort of cross-platform integration between light microscopy that users might be bringing in, the SEM images, and also taking this over to the TEM, which should aid the speed in identifying targets once it's loaded onto the Krios. So one final thing that I'm just going to briefly touch on, this is not something that's currently on the user program, but internally we've started looking into doing some micro-ED. So this is on our Talos instrument, and this is work done with several people across Diamond and also Thermo Fisher. So we've done initial samples with protein crystals that we've milled on our Scios, and we've installed C-to-D camera. So this is radiation hardened detector on the Talos. So we've have continuous rotation and collection of our samples. You can see one of our test data sets here from proteinase K. And from a single rotation, that's gone to 2.2 angstrom reconstructions. That's from, I guess, literally a few minutes worth of data collection. Now, in conjunction with the detector install, we've very recently sort of got beta version of the EPU-D software from Thermo Fisher. So that's got control over the stage tilt and the camera. It's very much a stripped down version of the familiar EPU interface. So set up imaging conditions, both real space and diffraction, atlas the grids, and then just need to input the increment to collect data from and click go. So it's been really quite straightforward. Now we're hoping later iterations of the software will have some batch acquisition to really speed things up. I should show very quick test data acquisition on a slightly earlier version of this program, with paracetamol, and yeah, we'll get some pretty beautiful looking diffraction from that. It still has to be processed though. So just finally, this is the EBIC team at the moment, plus two former members, Corey and Kyle, who left within the last year. Also thank everybody within EBIC whose work I've been presenting today, but also everybody within Diamond who we rely on for all of what we produce. And just to say, this is a team that's been rapidly growing and is continuing to grow, and we have job adverts out at principal EM scientist level and also senior support scientist level. And with that, I'm going to close. So thank you very much.
So perhaps a moment for one or two questions while Gerard sets up. Neil?
I suspect it would be. We aim to collect on all the Lamella that we milled. So one group did take their grids back after data collection. They've done full data collection. I don't know what success rate they had or what they wanted to do with them afterwards.
Okay, cool. Further questions we'll catch Andy on the grid. So, happy to introduce the next speaker is Gerard Kleva from the EMDB, and he'll tell us about what's new.